Welcome to the 59th Theoretical-Physics-Colloquium by Professor Anna Watts from the University of Amsterdam. She received her PhD from the University of Southampton in 2004. Then she had several postdoc positions. She studied with the NASA Goddard Space Flight Center and spent there a year between 2004 and 2005. Then she spent 2 years at Max Planck Institute for Astrophysics in Garching. She had another postdoctoral position at the University of Amsterdam between 2008 and 2009, and then became a faculty at the University of Amsterdam in 2009. Since 2019, she's a full professor at the University of Amsterdam. She is also active in professional service. She is a scientific editor for the monthly notices of the Royal Astronomical Society, a co-chair of the Dense Matter Science Working Group for the proposed Enhanced X-ray Timing and Polarization Telescope. In 2021, this year, she received Mid-Career Prize from High Energy Astrophysics Division of the American Astronomical Society. The citation reads for her trailblazing work in the understanding of neutron star fluid dynamics and developing and applying rigorous inference to obtain observational constraints on dense matter. Her research interests are in theoretical physics and more specifically in astrophysics. She's studying the physics of neutron stars, thermonuclear explosions, star quakes, magnetic flares, properties of matter at ultra high densities in ultra strong magnetic fields. She is also actively involved in development of future high energy space telescopes. And today she will be talking about a nicer view of neutron stars. And with that, I'll give the microphone to Anna.
Well, thank you very much for the invitation and for the introduction. It's very nice to be in Arizona, at least virtually, as a change from Amsterdam. So indeed, I'm going to talk to you today about NICER. NICER is the Neutron Star Interior Composition Explorer. It's an X-ray telescope. It's mounted on the International Space Station, and you can see it kind of just behind my head, this little box right there. That is NICER, basically, and you can make it as a nice add-on to the Lego International Space Station model as well, if you would like. NICER's goal is to study interior composition of neutron stars. So I'm going to start off with a little introduction to neutron stars and why they're interesting from a physics perspective as well as from an astrophysics perspective. So basically, neutron stars are the dead remnants, if you like, of massive stars that have come to the end of their lives, and the core has collapsed during a supernova, the outermost layers have been flung off, and you have some kind of compact remnants basically left over. They're not quite massive enough to progenitors to give rise to black holes, because then the collapse would be complete, but they stop just short of that, basically with a very ultra compact nuclear density star, perhaps 20 to 30 kilometers in diameter, containing maybe 1 to 3 solar masses of material. So extremely, extremely high density. This is our kind of basic idea of what a neutron star looks like. It has a quite complicated layered structure. Our picture is that the outer part of the star is a solid crust. And essentially that will be an ionic or nuclear lattice, with at least in the outer crust, most of the pressure coming from degenerate electrons. So it's effectively kind of white dwarf material. The nature of the nuclei themselves changes as you go deeper and deeper into the star. So you might have, for example, iron in the outermost layers, basically, and then getting more and more neutron rich as you increase in density and you force electron captures. I should also say on top of the crust, you can have an atmosphere or a fluid ocean of some kind, and I'm going to come back to talk about that in a little bit more detail later on. So for now, we're kind of halfway through the crust, continuing to go deeper and deeper into the star. The nuclei are becoming more and more neutron rich, again, through electron captures. And eventually, at some point, you will reach the point where neutrons start to drip out of the nuclei as well. So now I have a mix of, my lattice is still there. I have degenerate electrons still, and now I have free neutrons roaming around as well within the crust, and they are most likely in a superfluid state. So my solid crust just got a little bit more complicated. I then go deeper and deeper still, basically, and at some point, I've pushed these nuclei so close together due to the ultra high density that essentially isolated nuclei can no longer exist. The nuclei effectively dissolve into each other. They're extremely, extremely neutron rich by this point. And at that point, we reach the core, basically where the nuclear physics becomes more and more uncertain. Now, one possibility is that what we have in the core, basically as we go from kind of regular nuclear densities, if you like, up to perhaps several times nuclear density, we might simply have a very, very neutron-rich fluid. So something like 90–95% neutrons and a few protons and electrons in there, generally for balance, but still far more neutron-rich than we can create in laboratories on Earth. The other possibilities, which are very intriguing, is that because the gravitational confinement of the star buys you a lot of time, you have time for weak interactions to operate and to slowly convert matter basically into stable states of strange matter. Now, those can take various different forms. You could have strange quarks locked up in hyperons, basically within particles, and maybe have 10–15% hyperons forming in the core of the star. The other possibility is that the particles themselves are also forced to deconfine due to the high density, and instead I have some kind of deconfined quark mixture, again, most likely up-down strange quarks. And there are other possibilities like different types of condensates, for example, that might form, and I will say my nuclear physics colleagues are very creative in coming up with all kinds of entertaining possibilities for what might lurk within the cores of neutron stars. So here we really have a big question mark about the state of matter at such high densities. Now, to put this in a little bit of perspective, of course, we as neutron star astronomers are not the only people trying to understand dense matter or extreme nuclear physics and strong force physics. So I just want to set this in a slightly broader context for the moment. This is my insanely simplified phase diagram of the whole universe, where essentially I am showing temperature on the y-axis and chemical potential, or kind of roughly density, on the x-axis. Basically, everything around you, hopefully in your office right now, is down in this kind of lower left-hand corner, basically the region of normal hadrons and nuclei. And we would like to understand essentially what happens as we go towards the extremes of temperature and the extremes of density. There are some things that we can explore basically within the laboratory. And our colleagues who work in heavy ion collisions basically can look at, for example, what happens as you go to high temperatures, basically, and perhaps at kind of low to intermediate densities, what happens as you push material up towards deconfined quark states, for example. However, if you want to go to a completely unique regime, neutron stars are in this regime down here in the lower right-hand side. This is the low temperature and the very, very highest density regime, which you cannot explore basically within the laboratory. And for people working on neutron star mergers, they're a little bit above this, again, coming towards the heavy ion collision area. So what do neutron stars indeed bring you that's completely unique? Up to a few times nuclear density, potentially in the core of the star, highly neutron-rich material, which you can't recreate in the laboratory, and also the potential for stable rather than very short-lived states of strange matter. So it is a unique regime, but it is complementary to all of the work that's been done within the heavy ion collisions. And so one of the things that we look at is how to link up the work that we do to the work being done in that community. So that is our motivation, kind of big picture motivation of trying to understand all this fun and exciting nuclear physics. But we are neutron star astronomers, and so therefore we have to find some way, what can we go measure with a telescope that's going to tell me something about all of this very interesting nuclear physics. All of the techniques that we are using follow the chain of logic here. So let me start by walking through this. All of the unknowns in the nuclear physics are down in this lower left-hand corner. So that's the unknowns in the core composition, the types of particles that are there. Are we dealing with nucleonic matter, very neutron-rich? Do we have perhaps phases where there's hyperonic matter with some hyperons, or do we have deconfined quark matter? We're also uncertain about what the forces are basically between those particles on the microscopic level. However, those very microscopical behaviors, compositions, and forces influence on the larger scale what we call the equation of state. And that is the macroscopic relationship between pressure and density, basically within the star. And of course, you can put temperature in there as well. I'm going to largely ignore temperature in my talk because I'm going to be talking about old, cold neutron stars. But if you're dealing with newborn neutron stars or neutron stars that have just smashed into each other in a merger, you would have to put temperature corrections in there as well. I'm lucky enough not to have to worry about those for the moment. What I'm showing in the top left-hand corner are some examples of pressure density relations, current viable equation of state models for different compositions, different ways of calculating forces between the particles. This pale blue band here is a parameterized family of models that occupies essentially that entire band there as you change those parameters. So now I have pressure density. I still need to go towards something I want to measure, and there, thankfully, we can make use of the stellar structure equations. Because if I want to build a stellar model, how do I do it? I write down force balance equations, I ensure that matter is conserved, I have a continuity equation, I take an equation of state as an ingredient, I pick a central density, and I integrate out basically until I end up with a mass and a radius for that star. We are using relativistic stellar structure equations, Tolman-Oppenheimer-Volkov equations, perhaps with the rotational correction in there because these spin rather fast. But essentially, we are building stellar models. If we do that, we then change central density, we repeat the process, and essentially we change the overall mass and radius. So every equation of state, by doing this, translates into a mass-radius relationship. And you can see what those are essentially in the top right-hand panel on this plot. That basically you end up with different mass-radius relationships. And again, the parameterized equation of state would fill this entire band as you change the parameters. So you can basically say, all right, if I could measure mass and radius and map this relationship out, perhaps I can go back around this loop. So I still need to go one step further, because how do I go ahead and measure mass and radius? And here I'm going to take advantage of relativity as a tool, because the mass and the radius and the spin rate of the neutron star, which again can be very, very fast, several hundred times a second, those set the exterior space-time of the star. So any photon that leaves the surface of the star, for example, has to propagate towards us through this very dense matter exterior space-time. Okay, so it's coming through this very curved space-time towards us. As it does that, it picks up via relativistic effects the signatures of the mass and the radius. So provided I find the right observable quantity, those depend on the mass and radius, and now I can walk back round this loop of dependency and eventually hand my nuclear physics colleagues the answer in terms of the equation of state and ask them to tell me what it means in terms of the nuclear physics. So all of the techniques that I'm going to talk about today, and the one that NICER uses, depends on this chain of logic. What has been done so far in terms of this kind of loop? Well, for example, our radio pulsar timing colleagues are very, very good at measuring masses of neutron stars. They do that, for example, by taking a neutron star that's a pulsar where you can track its spin rate, and they take ones that are in binary orbits with other stars. As they move around, you can track the Doppler effects, and again, you can track relativistic effects if they're very close to each other. And they can use that to extract the mass of the system, although not at the moment its radius. So for example, they know that we have to make neutron stars of 2 solar masses. So every one of these mass-radius relationships gets up to 2 solar masses. And before these discoveries, there were other relationships that were down here that didn't reach that higher mass. So you can already cut down some of the parameter space, for example. And of course, now we have gravitational wave colleagues measuring tidal deformability of neutron stars, which is another way of deforming the space-time and a very, very similar technique. So now let me introduce you to NICER, to the telescope itself. This is a picture of NICER pre-launch in 2017. Basically, it is an X-ray, soft X-ray telescope. It has X-ray concentrator optics and silicon drift detectors, and it operates in what we call the soft X-ray band. So that's about 0.2 to 12 keV for those who know a little bit about X-ray astronomy. It's about twice the area of the XMM Newton telescope, which operates in a very, very similar waveband, but it has fantastic time resolution, absolutely top-notch time resolution. This gives you an idea essentially of how big NICER is. It's kind of a rather oversized dishwasher, I think. It's also one of my absolute favorite photographs ever of NICER, because I have 2 quite young children who are absolute huge fans of Lego Ninjago. And this for them was the moment where they said, oh, Mama works with ninjas.
Sorry to interrupt. Why?
Yep, go ahead.
Sorry to
Sorry,
interrupt.
go ahead.
Why X-ray telescope? Why not radio telescope?
So radio emission is typically coming from much higher up above the stellar surface. So at that point, you're out of the potential well, which means that all of these nice relativistic effects that we try to take advantage of are not relevant. You need to have emission from really right down at the stellar surface to pick up the imprint of these relativistic effects. And the X-ray emission that I'm going to be talking about is thermal emission coming from the neutron star surface. Okay, so there is NICER's size. NICER launched on June the 3rd, 2017, so it's just had its 4th birthday, launched on a Falcon 9, and it was then installed onto the International Space Station. There's some lovely videos online on the NASA site, basically, of the unpacking and install procedure for NICER. I said, if you haven't seen them, again, grab a cup of coffee, grab 10 minutes and go take a look. It's wonderful to watch, everything being unpacked and installed and put into operation. And of course, the very, very nice thing about having a telescope on the space station is that rather than just launching it off and never seeing it again, you can actually go make movies of it. So this is a film, again, rather sped up, of NICER actually on the International Space Station. And again, you can watch it moving around. It will move around in just a second so that you can actually see the detectors. Basically, here's the optics, and these are where the photons come in. You can also see that we're operating in quite a complex environment. So we've got solar panels moving around basically in the background that restricts some of the things that we can look at. We're tied, of course, to the orbit of the International Space Station. So there's restrictions there. Sometimes there are crew operations or spacewalks which get in the way of us being able to observe things, and NICER has to be stowed. Also, for example, for work on some of the other instruments that are around. NICER's been designed to withstand being kicked by an astronaut in case someone walks into it by mistake, which is not something you have to worry about normally for your regular X-ray telescopes. And every now and again, there is a conflict between a wonderfully exciting astrophysical X-ray transient and astronauts actually being outside the space station and NICER being stowed. That happened several months ago. And my Twitter feed was half full of people who love spacewalks and are really excited about astronauts, and half full of incredibly annoyed X-ray astronomers, desperate to see this kind of once every year event that had just gone off that we couldn't observe because the astronauts were wandering around outside. But this is the penalty for having something on the space station. The bonus is that it's cheaper. We get to take advantage of the infrastructure of the space station, the power, data transfer, and so on. So it makes it much, much cheaper compared to a comparable free-flying mission. Okay, now, let me go on to talk about a little more about the technique, essentially, that NICER is using. So I've already said we are looking for photons that are escaping from down in the potential well on the surface, being affected by relativity. What NICER is doing is also taking advantage of the rotation of the star. So we are using particular classes of stars that have a hotspot or 2 or 3 hotspots on the surface. So that as the star spins, the rotation actually changes. And then basically, essentially, we take snapshots as the star spins. And so we take advantage of the fact that the star is moving around and what we see essentially is changing. And then we go ahead and model that process. We understand extremely well how to model the space-times of rapidly spinning neutron stars. So that is something we can do very well. So given a hotspot of a particular shape and size and temperature on the surface, if we put in what angle we're looking at it from and what distance, we can predict extremely well for a given mass and radius what we should observe. And it's that process that we're using essentially to model to get mass and radius. You can see, for example, one of the relativistic effects illustrated in this movie here. In a weak gravity situation, if the hotspot goes behind the back of the star, it simply disappears and we see no emission from it at all. In a strong gravity situation, if the geometry is right, you can see on the right-hand side, the spot never vanishes because of gravitational lensing. And so you always see the back of the star, essentially. So that's the kind of relativistic effect, essentially, that we're exploiting to get the mass and the radius. Now, in terms of the specific type of stars that NICER is designed to look at, again, it's a soft X-ray telescope, so we need to look for stars that emit in that particular waveband. And we are looking at rotation-powered millisecond X-ray pulsars. These are very old neutron stars, born in a supernova. They've been in a binary system for a long time. They've been through an accretion phase where they've spun up through matter accreting from a companion. The accretion is now stopped. Some of them still have a binary companion around, and that can be rather handy because it means we can potentially get a mass measurement from radio timing. The system, they're often radio pulsars as well. But essentially they're, for all intents and purposes, isolated neutron stars. The X-ray emission is coming because of particles and return currents in the neutron star's magnetosphere. They tend to have very strong magnetic fields. So basically the particles and return currents are coming down to the surface and heating up the magnetic foot points of the star. And that is what is then giving rise to the emission that we see. So this is thermal emission coming from the magnetic polar caps of the star. They're fast rotators, again, a couple hundred times a second, which lets us take advantage, again, of the special relativistic effects as well. Now, let me walk you through in a little more detail exactly how the process of analysis works, because I'm going to go into some of the kind of weirdnesses that we've had to deal with while we do this. The first thing that we need is fantastic data. It's called pulse profile modeling. So what is a pulse profile? Pulse profile is what I'm showing here. It is basically making a histogram of counts, so X-ray photons, by energy channel and by rotational phase of the neutron star. So every photon that arrives, basically we essentially time tag it, we relate it to the spin period of the neutron star, which we're tracking, and then we record the energy and we drop it in a box. And over time you build up a pulse profile here where you can see essentially very bright pulse. And this is the rotational phase that photons preferentially arrive at. So this is the kind of data that NICER collects. We then, because we're going to be doing Bayesian inference, we need a model, a physical model of the process. This is where our relativistic ray tracing model comes in. And I said, we put basically essentially a hotspot on the star, and the idea is to generate a synthetic pulse profile for a given set of model parameters that we then compare to the data. So what do we have to put in there? The parameters specifying the exterior spacetime, the mass, the radius, for example, the surface emission pattern, temperature distribution, beaming function or atmosphere model. We have to put in the angle that we're looking at the star from, which we may or may not know in advance, the distance, any interstellar hydrogen absorption, some background components, and again, then the shape and location, basically in temperature of the hotspots on the surface. Those all go into our model. That generates a synthetic pulse profile, which we then are going to compare to the real data. One more step.
Question, please.
Yeah.
How long do these hotspots normally last?
They are essentially, for our purposes, they last an infinite period of time. They do not change over the course of our observations.
Thank you.
There are other stars where they do vary, but fortunately for these ones, they don't. And that's something that we've checked. Okay, we have one final step before I can compare my beautiful relativistic ray tracing model to the data, and that's it has to go through an instrument model. So one of the things we have to do is to understand how the instrument treats incoming photons for that final comparison. And then we basically have to hand over to a large statistical sampling code, because we now need to survey this whole parameter space, basically in order to get eventually posterior distributions on all of the parameters of the model. That means the mass and the radius, which is what we want for dense matter, but also all of the geometric parameters of where the hotspots are. And essentially, we are using this to make a surface map of the star. And these are stars that are, again, 20, 30 kilometers across, thousands of light years from Earth. And we're using X-rays and relativity to make a map of them. And that just, it blows my mind because I'm a complete map nerd. And I love the fact that we can do this basically with this technique. So now let me walk through some of these aspects in a little more detail. The first thing I want to do is show you some real pulse profile data. Both of these stars are also radio pulsars, and we use the radio ephemeris, so the spin model, essentially from the radio pulsar, to figure out the phase of arrival. What you're seeing on the left-hand side is the brightest source, the one we analyzed first, or not quite the brightest, the second brightest. In order to make this pulse profile, what you're seeing on top is the bolometric pulse profile, basically all of the different energy channels added together, 2 rotational phase cycles, and in the bottom is it broken out by energy channel. 2 very clear pulse profile, two very clear pulses rather in the profile, 1.9 megasecond of data to go into this. It's about 3-4 weeks of data built up over more than a year, basically this entire thing. Basically, this one, we have no binary companions, so we've no independent indication of the mass for this source at all, but this was the first star that we analyzed. On the right-hand side is the one that we did second, much lower quality data set in some respects. So many fewer counts overall. And you can see that also in the quality basically of the pulse profile broken out by channel. It's a very interesting source, which is why we bothered to do it, but it's one of the faintest, and this is really a stretch for exactly what NICER can do. This is again 1.6 megasecond of data to get to this point, really at the limits of what NICER can try. The data have some interesting things. One thing that we found quite soon was that optical photons, basically coming in and reflecting basically off solar panels at certain angles, actually mimic X-ray photons occasionally in the detector. It's a phenomenon called optical loading. I had never thought as an X-ray astronomer I would have to worry about the sun and optical photons from the sun, but apparently we do. So we had to make some cuts of what sun angle we took observations at, basically in order to rule those out, because we want to measure the pulsar and not the sun, and that was contaminating our data. So there's a bit of data processing goes on here to remove contaminated observations. Coming on to the simulation and inference codes that we use, I said there we did a lot of work within the collaboration to try and test or cross-test our codes, and that's something that's still ongoing and now more intensively. In terms of the relativistic ray tracing, we had about 6 different groups with different relativistic ray tracing codes, and we did a very extensive cross-testing exercise there that uncovered some errors in order to make sure that our relativistic ray tracing was being done correctly. And then we had some cross-testing exercises on the inference codes, so the large statistical simulations as well. This is way more computationally intensive. We need supercomputers. And when we first started off, there were only 2 groups with the resources to do this. We've now got other groups coming online, basically with cluster access as well. But we also did some cross-testing there. What I will talk about mostly today are the results coming out of my group. We use a code that we developed in-house called the X-ray pulse simulation and inference code. It's available open source and online, so if anyone wants to go and play with it, you're very welcome to download it and help to develop it or use it for any analysis. Coming on to the instruments, I mentioned this is really important. We have to fold our synthetic data through an instrument response to compare to the real data. And of course, that instrument effective area, which is what I'm showing here, is actually a little bit uncertain. And so in the end, this is something that we built into our models. We tried to model the uncertainty in the instrument effective area, and that's then a parameter in our model as well. So it's one of the things that we find eventually a posterior distribution for. And this has actually turned out to be rather important, and it's something we're now emphasizing for future missions as well, that it's not only understanding the response of your instrument, but the uncertainty in the response as well. Coming on to the, I guess, the most astrophysical part of it, of course, one of the other things that we have to do is to put in a model for the pulsar surface emission. You know, what shape are the hotspots? What kind of shapes do we allow? Where are they allowed to be on the surface? What kind of temperatures and temperature distributions do they have? So this is fun. You can go talk to your pulsar theory colleagues and say, you know, hey, what kind of shapes should we allow? And they will kind of laugh gently and say, we don't really know. There's a range of possibilities, and it is quite hard. You know, it's hard to simulate return currents in a pulsar magnetosphere. It's even harder to translate that into a prediction for a temperature map. And they will produce pictures like this one, where you can see potential return current distributions. So what we decided to do in the end is to try to parameterize our uncertainty a little bit. So my group in Amsterdam, what we decided to do was, you know, we're going to assume 2 hot regions, basically of some kind, because we have 2 clear pulses in the pulse profile. And we're going to basically gradually allow the polar caps to have different shapes and different temperature complexities. And we're going to work up through the sequence basically and see whether it matters. The way that we parameterize it allows, for example, circular spots, core annulus constructions, off-center annulus constructions, and then to have each individual hot region formed from 2 overlapping circles. And that in principle allows us to create crescents or something with a temperature edge. It's a crescent, for example, if you set the temperature of this one to be 0. And then the other hot region, you can force it to be antipodal on the opposite side of the star, or you can essentially allow it to move around freely. And that's something that we also try. And its properties can be essentially completely independent. So this is basically the sequence that we worked through basically in our analysis. And the idea was to, in a fairly simple way, capture the range of possibilities that our pulsar theory colleagues had come up with. So the first star that we worked on was the brighter one that I showed you. We ran through this whole inference process. We ran through the sequence of models. And out of that, we then identified a preferred configuration. We did that in basically a number of model comparison ways. We first of all just took a look to see whether the model, did it look like the data? What were the residuals? Did it look sensible? And that enabled us to rule out very quickly a configuration where the two hot regions are opposite to each other. It's a terrible fit for the data. We calculated Bayesian evidences. We looked at the predicted background and how it compared to constraints from other instruments. We looked at the maximum likelihood. So we had a whole range of model quality measures to identify the preferred configuration. Took us a long time also to build up the required data sets and work through all of these issues. So although we were installed on the space station in 2017, first results did not come out till the end of 2019. What you end up with are an enormous number of this kind of thing, corner plots showing posterior probability distributions. So basically, I'm only showing here a few of the parameters. We have these for every single parameter in the model. But what I'm showing here are the posterior probability distributions on the mass and the radius and the compactness, both two-dimensional and also one-dimensional posterior distributions. So we have, oops, let me go back. Basically, we have a mass coming out about 1.34 solar masses, which is pretty standard for a neutron star, without any constraint from the prior on what that should be, about 10% uncertainty. Compactness was incredibly well constrained, and the radius came out around 12.7 kilometers. And then, as I said, we can do model quality measures, look at the data, the model, and the residuals, and check whether that looks okay. So in terms of the preferred configuration, let me first talk about the sky map. So basically, this is the surface map, basically. So we are looking at the star from one hemisphere, and the two hot emitting regions are on the other hemisphere. And their shape turns out to be rather unusual. One is a fairly small spot, and the other one is this kind of long extended arc, basically. And as the star rotates, those give rise to the two pulses in the pulse profile that we see. So that's kind of fun straight away, because if I return to this diagram, on the top left is our kind of standard cartoon of what a rotation powered pulsar looks like, with this beautiful symmetric dipole field in which the two hot regions would be opposite to each other. So I think we can safely say, you can't get that. If your two hot regions are on the same hemisphere, that's not what we're seeing. And in order to get rise to that, you have to have some much more complicated magnetic field structure. It's possible, as it turns out, but it raises some interesting questions about the stellar evolution of, where did this field come from? Is it a remnant from the supernova and the progenitor star? Did it come through the accreting phase? It also poses interesting questions for the emission that we see. This star is not just an X-ray pulsar, it's also a gamma ray pulsar and a radio pulsar. And a lot of the radio and gamma ray modeling for this source so far has assumed that this is a perfect dipole magnetic field. So, we put our results out at the end of 2019 and said, well, okay, there are implications here for the multi-wavelength emission. And we need to now see whether it's compatible basically with those wavebands. And I was rather expecting, at least one or two pulsar theorists to turn around very quickly and say, it's just not going to work. You've allowed in your modeling too wide a range of possibilities for where the spots can be. You have to restrict things. However, the Princeton Pulsar group very rapidly came along with the paper where they looked at this and said, actually, you can have your kind of crazy magnetic field structure and we can still explain quite happily the radio and the gamma ray emission. So that was a really, really nice thing to see. And that's something that we're still working on. Coming on to the mass and the radius. So what I'm showing here are the 68% and 95% basically credible regions, basically for the mass and the radius for this particular star, with a whole bunch of different mass radius relationships, some of which I showed you right back at the beginning of the talk, just to give you some kind of idea of the possibilities. So what you can see, the uncertainties are still fairly large. The radius is kind of really right in the middle of the range. And I should also say there is an independent analysis team within the NICER collaboration led by Cole Miller at the University of Maryland. Their code makes different assumptions, has slightly different numerical techniques, but essentially they come up with an independent result as well, and their results were extremely comparable. Very slightly higher radius, but in general overlapping with our results. Okay, so that's the first result that we had. We showed that the technique essentially could work. Got a radius right in the middle of the range of possibilities. And then we had to come back basically and decide on a second source to analyze. We had intended to move on to analyze the brightest source in the sample. It's a little bit more awkward because it's an off-axis source. There's a bright active galactic nucleus in the field of view. You have to look off-axis, which means you need to work a little harder on the instrument response. However, end of 2019, our radio pulsar colleagues came along and said, hey, we've just found a 2.1 solar mass radio pulsar. 2.1 solar mass is the heaviest known neutron star. Very exciting from a dense matter perspective because it would have potentially the highest central density. So, we asked immediately, could we observe it with NICER? And yes, it emits in the X-ray as well. It's faint, so it's challenging, but really promising for dense matter. So we decided to spend time on this. We have the mass and distance and inclination from updated radio measurements from the Nanograv and Chime Pulsar collaboration, which is fantastic. And in addition to the NICER data, we also have some data from XMM Newton. Not phase resolved data, but it turns out to be very, very useful because it lets us get a good handle on the background for this source. So basically, we decided instead to work on this particular one. And we've just published our mass and radius results for this particular star. To give you first off an idea of the surface map, on the left is the first star that we did. On the right is the comparable surface map for the star we've just analyzed. This time around, we're looking almost directly at the equator with both spots in the same hemisphere again. Looking on the equator is the reason why we can actually get a good measurement of the mass for this star because we get Shapiro delay in the radio. Configuration is a little bit less extreme than for the previous star, but again, the spots are both in the same hemisphere. There's no evidence that one of them is this long extended arc, basically this time around, but certainly, again, they're not directly opposite each other, so it implies a slightly more complicated magnetic field. Coming on to the mass and the radius. This is a slightly more complicated diagram. This time around, I'm showing results for 3 different data sets. NICER on its own, basically, which is the phase resolved data set. XMM Newton on its own, which is not phase resolved, and then the 2 combined. So basically, let me start off first of all with the mass. So in the middle here is basically the mass that we infer. This is dominated by the fact that we have a mass prior, basically coming from radio timing. We know it's about 2.1 solar masses, and that determines basically the end result that we get out. It really doesn't move terribly much. However, coming on to the radius, basically what you can see, NICER only is this blue curve here at slightly lower radius. Once we add in XMM, we end up with the red curve. So the radius shifts up when we add in the XMM data as well. So what is going on there? Basically, what is happening is that XMM is getting rid of high compactness solutions. Because what it is doing is it is focusing on what's happening underneath this plot here. This pulse profile sits on top of a large unpulsed component, okay, that doesn't effectively vary. How do you get an unpulsed component? Some of it is genuine astrophysical background from things other than the source. In NICER, for example, that could be particle background around the space station, which is pretty high. It can also be other astrophysical sources in the field of view, which don't pulse at the pulsar frequency. But the other way of getting it is by having a lot of gravitational lensing. If you have a very, very compact star, even putting 2 spots on the surface, essentially because they're always visible for certain geometries, you effectively create an unpulsed component by gravitational lensing. XMM gives you a much better handle on what the true astrophysical background is. And basically says, yeah, this much comes from the star and this much doesn't. And what it tells us is that you've got to rule out these high compactness solutions because NICER would kid you effectively about how much background there is. And so XMM says, no, this is what the background is. You have to get rid of these high compactness solutions. They're not appropriate. You're attributing too much to the star. Get rid of it. And that is why the radius then shifts up, basically, when we incorporate the XMM data set. It's a smaller data set. It's a little bit more uncertain. We're sensitive to some of the assumptions that go in with how we combine that, but it's a nice demonstration of why that's so important. So putting now the mass and the radius together, basically with the other one, this is where the new result sits. And again, 68% and 95% credible regions shown here. So again, we find a radius basically coming from my team of 12.4 kilometers, uncertainties again around 10%. So what do you see? Well, first of all, there's not a lot of change between the two stars. The mass goes up by 50% and the radius does not seem to shift a great deal. It is really middle of the range. What you can see is that the low radii, so the very softest equation of state models that give rise to those, are strongly disfavored. Basically, so that is extremely important, I think. The higher models potentially could still be allowed, but these soft ones really are starting to be ruled out. This time around, the independent analysis that was done by the other team comes up with a nominal higher radius of about 13.7 kilometers, with wider uncertainties compared to our 12.4 kilometers. That we understand, I think, the reasons why that is happening. So for example, in the analysis that my team does, we don't allow in our pulse profile modeling any radii above 16 kilometers, because there are no equation of state models that would give that. The team led by Cole actually allow for the possibility of higher radii. XMM would potentially push you in that direction, so they get a higher radius coming out, but they incorporate that constraint later when they do equation of state modeling. We also have some differences due to the way that we incorporate the XMM data. My team are a bit more conservative in terms of the potential miscalibration between the two instruments. And if we make that a bit tighter, we would shift up a little bit in radius. And we also seem to be a little sensitive to the assumptions we make around the XMM background. So we have some differences, but essentially we understand quite well, I think, the reasons for that. And they're all areas that we can improve on in the future as well. So now we have to think about what does it mean for dense matter and for nuclear physics. So comparing these mass radius relationships is really nice, but what we really want to do is a second stage of inference, going through those stellar structure models, basically so taking the mass and the radius posteriors, working back now towards the equation of state parameters. And in doing this, we can take the results from NICER, but we can also start to incorporate information from nuclear lab experiments. We can incorporate information from gravitational wave detections as well. So all these things can start to roll in this second phase of Bayesian inference. So I'm just going to give you a kind of quick outline essentially of how that goes. First thing we have to do is to kind of specify an equation of state model that we're going to be testing. So we have to find some model for pressure as a function of density. There are a large number of parameterized models that people are using and some non-parameterized ones. The team that I'm working with, basically my group and also the team at TU Darmstadt, for example, we're using two high density parameterizations, one involving piecewise polytropes at high density, and one parameterization based on a model for the speed of sound, basically, and how that behaves in dense matter. And at the low density, basically, we're taking models informed by chiral effective field theory, kind of up to nuclear densities, and then bolting these high density parameterizations on top. And part of the reason is to understand our sensitivity essentially to those assumptions. And then what we're trying to do is to find out, what are the parameters essentially in these equation of state models by doing this inference. So let me show you kind of where we sit basically when we do that. So I'm going to show equation of state predictions in mass radius space rather than in pressure density, just because I think it's a little bit more intuitive. Of course, NICER makes individual measurements of mass radius, but doing the equation of state inference lets us put these into an overall mass radius function. So for the two models, piecewise polytropes on the left and speed of sound on the right, this dashed black line incorporates the 95% of the prior space, basically, although it doesn't show the distribution within that. Basically, once we put in, first of all, just the existence of a 2.1 solar mass neutron star, because that is the strongest constraint basically that we've had before this. You already start to cut down that space because you have to have an equation of state that gets you up to 2 solar masses. So you lose this space basically down the left-hand side. What I'm showing basically in red was that the first measurement that was made by the radio teams, 68%, 95% credible regions. They've now revised that mass down a tiny little bit, and that's the value that we use in our analysis. So we're starting off with the green distributions basically here. And again, you can see some slight differences between the two parameterizations in terms of the relationship. We can then go ahead to incorporate all of the other astrophysical information. So if I pop back to the previous thing, just from the mass measurements, we start at this green region here. Let's now, first of all, start by incorporating the mass radius measurement that we have for J0030, the first star that we analyzed from NICER, and information that we have from binary neutron star mergers and the associated kilonova, so tidal deformabilities. What you get then, oh, sorry, too far back, wrong direction, is that you move to these red lines. So everything shifts basically down to the left, and that's particularly driven by the binary neutron star merger GW170817, which favors softer equations of state. Then when we add in the latest NICER radius measurements for the 2.1 solar mass neutron star, we shift from the red to the green. So you can see everything pushing back a little bit towards the right. And then particularly for this parameterization over here, you start to rule out some of the lower radius space. So basically, by incorporating measurement after measurement, we are starting to hone in basically on the mass radius relationship, but there's still a little bit of dependency in here on the choices of parameterization, but that will gradually improve over time. And you can see we can start to make predictions for what the radius of a 1.4 solar mass neutron star is. We can also start to make predictions for what we think the maximum mass might be of neutron stars, although again, right now, this is parameterization dependent. And of course, one thing we're all very interested in is what is the nature of the 2.6 solar mass object that LIGO recently discovered, LIGO Scientific Collaboration. Is it a neutron star? Is it a black hole? Certainly at the moment, from what we have, it looks rather unlikely that it was a black hole, but there's still an equation of state model dependence in our analysis. So what are the next steps basically coming for NICER? We have 4 new sources for which we're going to measure mass and radius, and we're building up data sets and in fact are doing analysis already. One of the ones that is coming, and the one that will come next, is this one here. It is an extremely well-known 1.4 solar mass neutron star. It's in a binary. We have a radio mass measurement already. It's extremely tight and got tighter. So we are pretty sure that the radius is going to lie somewhere basically within this narrow band. So we're trying to get now a radius measurement for that one. Analysis there is ongoing. We're hoping to release that result this year. We're also going to update the 2 sources that we've done. We have more data already on this particular star, a much bigger data set, and we're reanalyzing the new and updated data set there. This star, we are hoping particularly to improve the background modeling now that we know it's so very important. The NICER team have their own background models of the space station environment that we're trying to incorporate rather than relying on XMM data. We've got XMM data sets to incorporate basically for this star as well. And we're talking with our pulsar astrophysics colleagues about possible surface pattern dependencies as well. And I said, the papers are on the archive. All of our analysis codes from my team are publicly available. Code, scripts, data samples. You can go try and replicate this, add things to the model and play around with this yourself as well. And the mission will run for at least another 2 years with the senior review to come this year. We are also thinking ahead to the next generation of telescopes that will use this technique. There are other classes of neutron stars with hotspots, accreting neutron stars. They are different source types. The hotspots may come about because an accreting ocean explodes on the surface of the star and part of it gets hotter than the rest of the star. They may also be accreting pulsars, basically where matter is being channeled out of an accretion disk towards the surface of the star. But again, it gives rise to hotspots. The beautiful thing about them is that they spin faster than the NICER sources. So the special relativistic effects are in principle stronger, and that should help us get tighter radio constraints. The challenge is that the surface pattern mechanism is different. They're also variable, so we have to contend with that as well. But they have other complementary techniques that can be applied as well, so we can cross-check things. So there's ups and downs in doing this. And there are plans now for future large area hard X-ray telescopes, because they need to be harder X-ray telescopes than NICER, to look for these free-flying several square meter X-ray telescopes to target these sources. EXTP is a joint European-Chinese mission that would do this, Chinese-led. StrobeX is a NASA probe concept that would also do this. So we're working on these plans for the next generation of telescopes to exploit this. So to finish off, NICER has basically pioneered this new technique of pulse profile modeling to get mass and radius of neutron stars. And again, we've got a lot of kinks in the process to work through. And we, essentially we finally managed to start delivering results. We've measured the size of 2 neutron stars, including the highest mass neutron star known. And I said, we're making maps of these, tiny, tiny stars, thousands of light years away, using relativity, using X-ray photons, using Bayesian inference. And it is fantastic to me that we're able to do that. However, I think probably my favorite achievement of the whole thing is that we've taken the NASA mission patch, which you're seeing here at the bottom of the screen with this beautiful, well-behaved, lovely symmetric pulsar, basically in the bottom right-hand side, and we've broken it. And I think that will go down as my favorite career achievement, basically no matter what comes for the rest of my career, is that we managed to trash the NASA mission patch. I will stop there and I'll take any questions.
Thank you very much. Thank you very much. Thank you for trashing the NASA logo. It seems cool. So anyway, let's go to questions. Do we have any questions right away from the audience? Please, Ignacio Bombaci, go ahead. You have to unmute yourself.
So, okay. Thank you. Oh, so beautiful talk, Anna. Thank you very much. I have a question. How can you reconcile this radius determination for this object, J0030 and J0740, with the one which has been derived for the quiescent low mass X-ray binary X5, which is around 9.5 kilometers?
It is not easy to do so. And I suspect it is a model dependency in particular. So the technique that's used to do that is a rather different technique. It's phase average. So you're not thinking about the rotation. It's quite dependent on the distance, the composition, basically you assume, and we are much more independent of composition assumptions, basically in the modeling that we do, fortunately. So I suspect it is some kind of systematic effect basically in that system, given the technique that's being used, basically that's pushing that radius down. But this is actually, so one of the things we want to do with the accreting stars is we can potentially use that phase average modeling technique that's been applied on stars that then also have, for example, a couple of different types of hotspots through accretion or thermonuclear bursting. And we can actually apply all 3 techniques to the same star, and that will really let us get a handle on any systematics. So you mean, I don't think I can reconcile it actually.
So you mean those values for the radius, we have not to trust those values.
So
also for example, for X7, another.
Yes, there's some of the results coming from phase average spectral modeling. So for example, the burst spectral modeling by, for example, Jonas Natila and his collaborators is coming out with consistent results basically to what we are getting. Some of the results are not, but there are known systematic uncertainties in the modeling. For example, the effect of residual accretion, potential magnetic field effects in the atmosphere. So there are other things that might be playing a role there that give you a systematic offset. Now, it is completely possible that we have a systematic offset in our measurements as well. But I think it's hard to reconcile them without there being some systematic uncertainty basically in the technique. But for the phase average modeling, there are known systematic uncertainties that could lead to that kind of offset.
Okay, thank you very much.
Okay, I think we have a question from Patrick Miles. Do you want to ask it yourself?
Yeah, sure. Hi, Professor Watts. So I wanted to ask about incorporating XMM Newton measurements into the NICER analysis of J740. I maybe you mentioned this already, but you said that it reduces like the unpulsed background in the signal. Does it also remove unpulsed signal from the star itself, from the fact that kind of you're always seeing the hotspots due to the relativistic effects?
Yeah, so basically what it does is it tells you, what's the true astrophysical background. So XMM is in a very, very different particle environment. So it's possible to get a kind of good blank sky background basically for XMM, and then observations of the star itself, and to compare those two. And then basically on your pulse profile from NICER, you have an unpulsed piece on top of which sit the pulsations. And it basically tells you, what's the source of that unpulsed piece. And what XMM says to you is that, okay, you know, it cannot be coming from the star. It is absolutely, definitely coming from real astrophysical background, because I can go measure that really, really well and compare that to observations on the star. And, you know, left to its own devices, the NICER data alone would allow you the possibility of creating that from very high compactness solutions. Basically where, you know, the geometry is such that you mimic the emission from the hotspots, then contributes to that kind of overall unpulsed level. And what XMM tells you is, you know, sorry, you're not allowed to do that. This is really genuinely coming from other stuff. So you put effectively a minimum level of background that comes from other things into the modeling. And then when we incorporate, you know, we then develop one model that has to explain both data sets, and it just rules out a bunch of the solutions basically and kicks those low radius solutions out.
Okay, great, thank you.
Okay, next question is from Renee Belwood.
Yeah, let me just also try to turn on my camera. Very nice talk, thank you very much.
Thank you.
I was wondering, it seems like the real improvement in order to distinguish certain equations of state will have to come from an even better radius measurement rather than a mass measurement, because they are all conveniently lumped together over the certain region that you've shown. Is there any chance to further improve on the radii? I mean, you said, for example, that you measured 1.6 megaseconds on the one star, and that's really bringing it to the maximum that you can reach with NICE. Is there anything that one can do in terms of statistics or so to improve on the radii measurement?
Okay, so overall, there have been calculations. For example, there's a really nice paper by Dimitrios Saltis and collaborators in 2014, where they looked, you know, for simple models at the scaling with the number of photons of the constraints that you would affect. And it should scale roughly as the square root of the number of photons. So as we collect more photons, and we're still observing these stars, we're still building up the data set, as you increase the number of photons, essentially you should be able to improve the radius constraint. So for 0030, the first star, we've already got about a double size data set. We're reanalyzing that now with better instrument models. And so basically we can expect an improvement in the radius for that star, I think. The star with the very, very tight mass constraints, the mass constraint's about 3% uncertainty on that one. And that will help us to get a tight radius constraint for that one as well. So I think 0437, which is the next one that will come, unless something really strange shows up in the next set of analysis we're doing, that should give you a radius constraint of a few percent. Basically, so NICER itself will certainly improve. And then again, that's also the logic for going to this next generation of larger instruments as well. Again, you just collect more photons, and by doing that, and they're faster stars, everything scales with the spin frequency of the star as well. So in principle, you can look for favorable geometries, fast rotators, and we hope to get maybe 20 measurements, 10, 20 measurements, a few percent accuracy as well. So I think that there's good prospects even with NICER and even more with the next generation of telescopes.
Okay, next question is from Henry DeJong.
Hi, fantastic presentation. Thank you.
Thank you.
I enjoy with the idea with you kind of breaking the mold a little bit on that nice, pretty picture of the bipolar model and the spots being where the hot spots or regions being where they are. Do you think they're in the process of moving, or what would be a time frame on that, or and so forth? I mean, that's really interesting.
Yeah, so this for me, again, you know, our technical motivation is the dense matter, but I just think this is the coolest thing to come out of the results we have so far, actually. The timescale for evolution should be very slow. Absolutely not on the timescale that we're taking observations. So, you know, over the course of any NICER observation we're going to do, they shouldn't move because the overall processes that govern magnetic field evolution are relatively, you know, are really, really slow. And they're relatively low field neutron stars. So again, there's nothing like a strong field magnetar where the field is evolving relatively quickly. You know, we're talking millions of years for anything to even remotely change.
Right.
But then, as you said, the question is, where does it come from? It seems from talking to supernova people, they are all relatively happy with the idea of creating weird magnetic fields, basically from birth. But again, these are also really, really old neutron stars. So could that field structure survive through the whole phase of the life of the neutron star, through an accretion phase and out the other side? And it must have done, basically, to get to what we see. So yeah, there's some really interesting stellar evolution calculations now to come in. And again, so much neutron star evolution, you know, what did these things look like during the accreting phase? all those things tend to assume a dipole field. So for example, there's a PhD student in our group now looking at what would this look like when it was accreting if the field structure was like that.
Right.
It would look quite different, I think, to what we expect.
Yeah, that's a very opens up a lot of questions. Thank you so much.
It does. And on the shorter timescale, so the accreting stars, there we do have to worry about things changing on days to seconds timescales.
Right. Yeah. Thank you.
Okay. Are there any other questions from the audience? I do have a quick question myself concerning this magnetic field configurations and everything. There is apparently a lot of uncertainty about the location and the shape of this spot. So my simple question is, how much of a resolution you could achieve, for example, if you model those with some kind of like, I don't know, spherical harmonics to not have any prior constraints on what it should be, but rather to measure what it is? Is there a way of truly resolving the map?
This was my original idea to try and do this. The problem is the number of parameters you need. So this is really computationally intensive. And so far, we haven't found a good way of describing things with fewer parameters than we have for these fairly simple parameters models, which already take, a couple of 100,000 core hours on our supercomputer to run. One of the things we're playing with is dropping resolution a little bit to see if we can go to a more general pattern to try and do this. We're also looking at what ways that we could potentially make the code faster. And again, the code is open source. If anyone has brilliant ideas of how to do this, please jump in and have a go at it. Because indeed it would let us go for a much more general surface pattern and actually try and fit this instead. And that would be wonderful if we could do that. But yeah, right now it's purely a question of computational limitation of these simple models we can run, with up to 16, 17, 18, 19 parameters in total. Once you put spherical harmonics in, we found we need to add more harmonics in order to get a good description, and it becomes computationally intractable.
I see. Well, I hope there will be progress there. So we have another question. Udita Shukla, if I pronounce that correctly. Go ahead.
Yes, thank you. Yeah. Hi, Anna. My question is, what is the average or approximate area of a typical hotspot? Has that ever been measured?
Yeah, so hotspot size is something that we measure. So yeah, basically we can have, relatively kind of small angular size, 5-6 degrees, basically for some of them. To the degree that, in fact, we're not sensitive really to kind of substructure in the spots. Or as you saw, if I put the sky map back up again, you can get an idea for where did it go? Okay, there you are. So this is showing the actual angular size that we're inferring, basically for the two different stars. So, these are relatively, no, I wanted to put that on to play. Is it going to do it? Yeah, okay. So basically you can see, this arc is rather long, basically, and is extending quite a long way around, but it's very thin, and that's about the thinnest we could actually resolve, basically given our surface meshes. But the size is one of the parameters in the models, and one of the things we've tried to do is to provide posterior distributions on the geometries as well, because of course this is just one representation. In fact, these things of course have a distribution. This is not the only answer. You can allow these spots to be a little bit bigger. They can have slightly different shapes. And so we've tried to provide some better parameterizations for those, for people who want to try modeling possible surface patterns.
Okay, and my second question is, what would be the difference between, other than the typical lifetime of a hotspot, in an accretion-induced neutron star, which is in a binary system, which is still, say, old, and an isolated neutron star? Right,
so for doing pulse profile modeling, the major difference is the emission mechanism. So this is, if I try and find, hold on, let me flip to that plot. Where is it gone? That's the one I want. Okay, so basically if we're dealing with an accreting pulsar, so now we're treating material streaming in basically from the accretion disk along the magnetic field. So there are now a bunch of other things we have to take into account. Firstly, we have an accretion disk, and there can be a reflected component from here that gives a little bit of a pulsation, but there's another component, it's the emission in there, that's a little bit out of the potential well and off the surface of the star. The hotspot is primarily coming down here. So there's some emission from the surface where matter impacts it. There's also an accretion shock somewhere in here at a height, which is a free parameter of the model, most likely, a little bit out of the potential well. So that gives you a nice additional challenge for pulse profile modeling, because you have to put in the height of where some of your emission comes. You have to think about the beaming function in the relativistic shock. Sorry, yeah, in the accretion shock as well. You've got, again, your accretion disk might obscure emission from the other side of the star. So that's something you have to factor in. And these things vary, certainly on timescales of days. So one question is, okay, do I chop it up into lots of shorter segments? And I assume that the position of the spot might vary because I don't allow mass and radius to vary. Or do I try and model that movement somehow and include that? And that's one of the things we're now looking at in the group of, okay, we know how to handle NICER now, which is beautifully stable and has a specific emission mechanism. Now we're going to make it more complicated. And what does it do?
Okay, thank you.
Okay, next question from Matthias Halsten.
Yes, hello, can you hear me?
Yep.
Yes.
Yes. Yes. So my question is in respect to your impact of the on phase transition in compact stars.
Mm-hmm.
So for me, I think the results of the high mass stars have a lot of impact on probably the exclusion of a strong phase transition happening at low densities, or twin stars, low mass twin stars. Could you maybe comment a little bit on this?
Yeah, so I mean, this is really the bit where I kind of hand off our results to those who are more expert basically in what it means. So yeah, I agree with you. There are implications for phase transitions. And I think at this point, I would leave it to the experts to tell me, what does it mean in terms of specifics of composition and specifics of models. But I know that people are looking at this. Our mass radius posteriors are all available online for people to try with their own models, basically, and to look at the implications. But yeah, this is really not my area of expertise. So I defer to those who are working on it.
Okay. We have another question from Henry de Jong. Go ahead.
Hi, yes. Just curious, did your revised modeling using GR on the gravitational lensing aspects of the neutron star, did that get really revised or reinvigorated with the event horizon picture of the black hole? I'm just curious about if the two are kind of somewhat related.
No, I mean, we're all using GR in different ways. The only thing it came up with is I was having been on a radio show to talk about some of this stuff. I then got asked to comment on the EHT, which again is I don't do anything on, and it was kind of fun to be asked to comment on black holes when this is absolutely not something that I work on. But no, apart from being two beautiful manifestations of GR, that's the only connection.
Okay, thank you.
Okay, I don't see any raised hand. I do have one simple question. Obviously, NICER was not designed to study magnetars, but I'm wondering, where is the bottleneck? Why wouldn't you?
Actually, NICER is studying magnetars. Basically, so there is a magnetar working group as well. We don't do pulse profile modeling for magnetars because they're too slow, and the beaming function for magnetar is a nightmare because of the very strong magnetic field. And all of the QED effects that you have to put in there. So that becomes much more challenging. So you're not going to get mass and radius, I think, from pulse profile modeling of a magnetar. You might learn something interesting about where the spots are and the magnetic geometry, but it's going to be, you wouldn't get mass and radius because they're just too slow as rotators. And there's too much uncertainty, I think, in the beaming and atmosphere model. But NICER has a thriving working group looking at magnetar physics. They're taking observations of the new magnetar right now. And measuring pulse periods and measuring the spin evolution. So plenty of stuff going on there as well.
So what exactly you think is possible to extract from those measurements? The strength of the field, for example, the configuration of the field, those are okay?
In terms of pulse profile modeling, so yeah, in principle, you can apply the same technique to anything where you have some kind of hotspot, you put in some kind of atmosphere and beaming model. And I know that there are groups looking at using the XPSI machinery, so the relativistic ray tracing, and building in, a proper magnetar atmosphere scattering model, basically, and again, putting hotspots on the surface, perhaps coming from inside the star related to the field geometry and trying to do modeling. But I said, I think they're not going to necessarily give you mass and radius, but they could very well give you information about constraining the beaming function uncertainty and constraining the field geometry and the location of the hot regions. I think that would certainly be possible. So yeah, my group are not working on ourselves, but I know that people are using our code to try and do this.
Are you aware if there are any published analysis of that yet?
There are some people who've tried. How much would be published right now? I'm thinking of groups like Matthew Baring's group, basically are doing things. Roberto Sorolla, Silvia Zani's group, people like that are looking at it. Nobody has published a magnetar analysis using our pulse profile modeling code yet. But certainly plenty of groups have the capacity to do this and could very, very, very easily try and do it and adapt the work that they've already been doing. And of course, some of them have their own relativistic ray tracing codes already, because again, they don't need the rapid rotation machinery that we have. They don't need to worry about ablateness of the neutron star, which we do in our analysis, because they're simply not rotating fast enough. They're really slow rotators.
Okay, yeah, that's right. Thank you. Okay, I think I don't see any other questions. So using this opportunity, I would like to thank Anna again for a very nice presentation, for taking time to answer all of our questions. Thank you very much.
Thank you for having me.